Cool. So over the course of my internship, I've been working on profiling Clang in order to increase performance while compiling the Linux kernel. So I'm going to be talking about that and then some extra stuff that I've done along the way. A lot of the presentation is going to be essentially tips and tricks for if somebody else wanted to do this themselves, how would they do it? What have I learned over the course of the summer? So I've named the talk Profiling Clang plus Extras. So this is the contents of the talk. So Perfetto and LLVM, Linux perf, Clang-tidy, and then some fun bugs. So starting off with Perfetto and LLVM. So Perfetto, if you don't know, is an event-based profiler for performance tracing. So this is essentially a replacement for Chrome tracing. And they have like a C++ API exposed that you can use to instrument arbitrary C++ apps in order to trace them. So I've used Perfetto on Clang in order to generate traces of compile times for the kernel. So this is what one of those traces would look like. You can see on the left, it's like translation unit names, and then each like trace is broken down by time. So if you were to click on one of these process names, you would get, oh, I just skipped like 3 slides. Okay, you would get something that looks like this. And so you can see like it breaks it down into front end versus back end. It breaks down each source file that's being included. It breaks down like the actual optimization passes in the back end. And it's super useful for seeing exactly what's going on when you're compiling a translation unit. So essentially, like, why should we care about using Perfetto? First of all, it has a shareable links feature, which is super useful when you're like trying to collaborate on this stuff. So you can just like click share link and you would get a link to the entire trace, and you could just send that to somebody and they would open it and they would see exactly what your trace looks like. So there's that. The traces can also be easily concatenated. So if you just have 2 traces and you want to append them together, you can just do like Unix cat and just call like cat trace1, trace2. And then you will get one like appended or one aggregated trace. The trace events are user defined. So these traces or these trace slices can be like span multiple functions. So if you saw in the trace that I had, one trace just says front end, and it's like the entire front end of the compiler. And then the traces can also be more granular than that. So you could have traces that are like a part of a function, which is fairly useful if you're trying to actually investigate why something is slow. There's also a built-in query engine that comes with Perfetto. So if you're on the Perfetto like trace UI, you can just click this query engine. You can type in SQL queries, and like you can analyze the data of all of your traces using SQL queries. Perfetto is browser agnostic, which is useful. I think Chrome tracing was limited to Chrome. And then traces are quite a bit smaller than other profiling tools, which is useful if you're doing a lot of them. So this is the query engine that I was talking about. So you would type in a query at the top, and then you can do cool analysis on your data and like export it as a TSV if you want to like graph it or something like that. So here I'm doing like a like front end back end ratio sort. So essentially like which translation units take a weird amount of time in the front end. And you can see it's like, oh, this translation unit takes 2 seconds in the front end and 5 milliseconds in the back end. That seems somewhat suspicious. Why is it doing that? So you can do all sorts of interesting analysis with the query engine, which is super useful. I've linked sample traces on here. If you want to look at the slides later, and you go to one of these links, you will get like a kernel compile of x86-64 and ARM64 def configs. And then here's one of those queries that I mentioned. The queries get fairly verbose, so I wanted to like document at least one query so somebody doesn't have to go rewrite this themselves. Yeah. So the implementation of the Perfetto integration with Clang, it's already integrated in the LLVM build system with this patch that I submitted. The patch has not been accepted yet, so if you want to get like a Perfetto built Clang binary, you would have to like check out this patch and build it yourself. But there are 3 macros that you use. It's LLVM trace begin, LLVM trace end, and LLVM trace scope. So these start and end trace slices, and then the scope one starts a trace slice in the current scope, and when you go out of scope, the trace ends. So if you want to play around with those yourself, like this is what you would use. And if you want to build it yourself, you would just check out the patch, build Clang with -d Perfetto equals 1, and then just build it. So here's essentially what I've been using to build Clang. And then when you actually go to use it, you pass a -Perfetto flag, and then it uses the output file to determine how to name the outputted trace file. So if you were outputting a.o, it would output a.pftrace. There is currently a bug with this where if you have -no integrated AS, it outputs to /temp/a.pftrace or something similar to that. And since the Linux kernel uses this no integrated AS like everywhere, kernel build traces end up being outputted to /temp. So that's just something to keep in mind if you want to build the kernel with a Perfetto instrumented Clang. And then this is what I was using to generate those large, like full kernel invocation traces. So I just build the kernel with -Perfetto passed to every Clang invocation, and then I move all of the trace files to a single directory, and then I cat all of the trace files together into one big trace. And then you just load that into the Perfetto UI. So again, if you want to do this yourself, just go look at my slides. So that's Perfetto plus LLVM. And then I've also been using Linux perf. So Linux perf is another performance tracing profiler. Instead of being event-based like Perfetto, it's sample-based. And it works specifically at a function level granularity. So depending on your use case, it's more or less useful. So this is how I was invoking Linux perf. I have --no inline and --no children added to the perf report because no inline makes the UI load much faster, but it doesn't try to like unwind inline functions. So a problem that I was running into a lot is the traces take a really long time to load with Linux perf when you're doing like a full kernel make invocation trace. So --no inline makes it take like significantly less time. It went from like 30 minutes to like 2 minutes or something like that. And then --no children is useful if you only want to see leaf functions. So it's fairly useful when you're doing like analysis of why things are slow. So this is what a trace for Linux perf looks like. Yeah, I don't think, yeah, that's what it looks like. So Perfetto versus Linux perf, like why would you use one over the other? So Perfetto, the traces are much smaller. They're like 50 megabytes versus 5 gigabytes. And I found that Perfetto was much more useful for finding like compilation outliers rather than like generally slow functions. So using like the query engine, it was really easy to find like slowdowns that are just like kind of weird and then the traces are easily shareable. But I found it was difficult to find like general slowdowns, like for example, like a single function that's causing like a large slowdown in the code base. So Perfetto made it really easy to find like low-hanging unique slowdowns, but not necessarily slowdowns that would greatly increase the compiler overall speed. And then Linux perf, on the other hand, made it really easy to find functions that are just generally slow in Clang. Unfortunately, a lot of these functions are already known to be slow and were already optimized. So maybe there could be more optimization to be done there, but a lot of them are already known that they are slow. Furthermore, the Linux perf traces take a very long time to load. They're somewhat hard to share because you just have to send the trace file to somebody else. And then like compilation outliers don't really show in the trace because it's not broken down on like a translation unit like level. So Linux perf was useful for finding general slowdowns, but the general slowdowns were harder to fix. Perfetto was useful for finding like low-hanging unique slowdowns that were really easy to fix. So for example, with Perfetto, I found things like macro expansions that are like millions of characters long that cause like huge front-end slowdowns, and then the back-end takes like no time at all. Or I found like inlining of large functions being like reused over and over. So those functions would have to be re-optimized every time that they're inlined. And that was causing like large backend slowdowns for functions or for translation units that had like a small amount of front-end time. And then with Linux perf, we found regressions in compile time. So there's like when computing x86 CPU feature dependencies, there was a regression that was taking like 13% of kernel builds because it was just recomputing these dependencies every time. And when we like started caching those feature dependencies instead, we like completely reduced that 13%. But a lot of the other top functions that we found in Linux perf are like fairly hard to optimize. That one was just like a build regression, so it was easy to optimize. So that's mostly it for like Clang profiling. So now I'm going to talk about Clang-tidy and then the kernel. So Clang-tidy, if you're not aware, is a linter that uses Clang front-end actions. So it's usually used to add codebase specific warnings for like interface misuse and style issues. And I've been working on adding Clang-tidy in the Clang static analyzer as make targets. You can see the patch there. So like why use Clang-tidy in the first place? Clang-tidy, because it uses Clang's front-end actions, it gets access to Clang's AST and source manager. So you can essentially implement any Clang warning that you want in Clang-tidy if you really wanted to. So it's super helpful when trying to implement some sort of like style check or like code-based warning or something like that, because you can just reuse Clang's code and you don't really have to write anything yourself. You just like look at the Clang documentation and then just immediately write a check from that. So if you wanted to go run the Clang static analyzer or Clang-tidy, there's a patch to make targets for these. I don't think the patch has gone through yet. So when it does, you could just run like make Clang-tidy or make Clang analyzer. And then so that's it for Clang-tidy. And then this is just like some fun bugs that I found along the way of summer. So I think the first thing that I did this summer was fix like a Risc-V boot issue. So the problem was like Clang built Risc-V kernels weren't booting. And if you go look at like the kernel log, it's like it tries to run init, and then when you're calling exec for init, it returns like a text file busy error, and then the kernel just like stops. So after debugging for a while, I found that the kernel is trying to call deny write access in exec, and deny write access calls atomic dec unless positive. So atomic dec unless positive was not working properly, and I eventually found out that the atomic code in Risc-V was broken with Clang. So the atomic code is just like a bunch of inline assembly, and I think Risc-V atomic instructions specifically use 64-bit instructions. So all of the atomic code was using 64-bit instructions, yet 32-bit ints were being passed to the atomic code. And GCC just happened to work in this case. It kept, so it has like 0xFFF and 0x0FFF. So the one on the left is GCC, the one on the right is Clang. So those are both 32-bit -1, but only the one on the left is going to work with the atomic code because the atomic code is using 64-bit ints. So these are both valid code, but Clang happens not to work because it truncates the top 32 bits. And the fix here was just casting some stuff to longs after debugging for like several hours to figure out why this was happening. I thought this was a super cool bug. So then another bug that I had to fix was ARM unwinding. So there's an ambiguity in ARM32 stack frame specifications. So I actually fixed a similar issue in the kernel last summer. It's essentially the same problem, but in a different stack unwinder. So with Clang, it stores only the frame pointer and the link register in function prologues. But with GCC, it stores the frame pointer, stack pointer, link register, and program counter in function prologues. So the stack frame layout is like completely different between Clang and GCC. So it seems fairly obvious that this would break stack unwinders that try to unwind based on the frame pointer. So this ended up just being like some messing around with the values in order to get it to unwind properly. Yeah, I thought this one was also particularly cool, so I included it in the presentation. Yeah, so that is the whole of my internship. I'd like to say thanks to Nick and my team. I had a good internship despite the circumstances. Yeah. Does anyone have questions?
Huck, I was curious about when you're talking about pros and cons of Perfetto to Linux perf, you mentioned some compilation oddities. Mm-hmm. And I think on a later slide, you alluded to like macro expansions being particularly troubling. So I think what's interesting is, yeah, so that 1,000,000 character macro expansion, if you flip back to the other slide that has the perf output, so that source manager get file ID local,
yeah,
those are actually the exact same bug. So one of the things you showed was the perf report invocation with -- children or something like that.
Yeah.
So that's doing a bottom up profile as opposed to a
mm-hmm.
top down. But when you talk about the anomalies for certain compilations, can you describe for us maybe some of the files that you found that had very odd ratios of front end to back end, and why they were unusual compared to others? So I think you mentioned like a file that has always inline, but
yeah.
Can you remember thinking there's like one file in particular that was like very, very small function where it had the largest ratio, I think, of time spent in the front end compared to the back end.
Yeah, I think that was like crypto certificates or something like that. Essentially, it didn't generate any code. It was just like a long array of constants. So it took like 0 time in the back end, but it took quite a bit of time in the front end to actually parse the like arrays.
I would guess that in this list you have right here, it's probably check ice is what I would guess.
Mm-hmm.
You know, it's probably checking that all these elements are like constant expressions or integer constant expressions, maybe. But cool. And then maybe feedback for us. You know, what in this list here, maybe in particular, you know, maybe what should we investigate next in Clang or LLVM?
Yeah, I mean, I think like get file ID local at the very top might be the next thing to look at. Perhaps there's like something that's like easily fixable there. I'm not really sure. I haven't looked into that code like a ton. I know there's quite a bit of comments in that code that it's like this is performance like dependent. So I think that code is probably fairly optimized, but maybe there's something that was missed. And then I think the lookup bucket for is just like string map lookups, and that seems to be very high. So I don't know if string maps are just being used like everywhere, and maybe those could be like the results of those map lookups could be cached somehow. But the like string map lookup implementation as the second highest function in the trace seems somewhat suspicious to me.
And I was surprised by a lot of this work because a lot of feedback we hear from folks working on, say, like the Risc-V compiler for the Rust language, you know, will say, oh, you know, LLVM provides so much overhead for us. It's so slow. And yet when you started doing these traces, you found kind of, at least when compiling with Clang, the opposite is that it seems like Clang is a lot heavier than LLVM at this point by a lot.
Yeah. I should have included that graph of like front end versus back end time spent when compiling.
Cool. And then finally,
like the front end.
Oh, sorry.
Like a lot more time ends up being spent total in the front end than spent total in the back end, which is interesting.
And then question, will you be presenting this work anywhere else?
Yeah, so Linux Plumbers next Thursday, I'll be talking about Clang compile times and Clang-tidy. So yeah.
So, great presentation, Nathan, and thank you for all the work that you've done in your internship. There's a bunch of questions that I have. Have you looked at adding Clang-tidy to all of the Linux tools so that we can use it with things like libbpf and perf and other things? I run into bugs in that code all the time, and it'd be great to have Clang-tidy.
Yeah, so mostly during the summer, I've been adding it to the Linux kernel. I don't think it would be particularly hard to add it to another code base. Most of the difficulty of adding it to a new code base is just getting people to agree to actually adding it. I've had like a fair amount of resistance of like why do we want this in the first place? But yeah, I mean, to add it to a code base, you just have to get like a compile commands.json file and then just run Clang-tidy with it.
Okay, so the Linux kernel has kind of like shared build infrastructure and so on. So I wonder if like some of that could carry over.
Yeah.
Another question was the Perfetto traces are going to be wall clock time based, whereas the perf ones are going to be user time.
Yeah.
And so have you looked at looking at off CPU time for the LLVM compiles?
So the Sorry, what do you mean? The Linux perf traces are CPU time. So I guess there is that trade-off there between Perfetto and Linux perf, but.
So for example, if Clang blocks on a lock, then there's going to be no more kernel samples on that thread because it's blocked on a lock and it's not doing anything. However, wall clock time is going by, and so the normal way in kind of like Google 3 is that there are things like contention Z and so on where there are dedicated things which capture when locks are held. A thing you can do with perf is you can put trace point events on scheduling. Another way is using BPF programs, but both of them give you kind of off CPU flame graphs. But I'm guessing from kind of like me having to talk about it that it is not something you've looked at.
Yeah. So as well, I should probably mention Perfetto has like a system-wide tracing thing. I didn't really use it that much during the summer, but you can trace on like scheduler events. So it will like show you when your thread gets like descheduled and rescheduled. I just didn't really use it because it seemed to provide way more information than I actually needed. But it is possible. Like it does work.
I think that kind of like leads us to like a final question, which is, have you looked at like combining the perf data with the Perfetto traces and having kind of like a single kind of like source of truth?
Yeah, I mean, I've like considered it, but I don't really know how I would aggregate the two traces together. Essentially, like I'm just using the tools provided to me, not like writing my own tool. So like I'm sure if I really wanted to, I could combine them into like a single UI with like Perfetto data and Linux perf data. I just haven't done so. I've just been like switching between the two to look at both. Yeah.
Thanks.
It might be interesting as well to look into some of these allocations that start to appear up top, like seeing int free and C free from glibc in the profiles. Like I know we can disable doing any work, like actually freeing memory. There's a flag for Clang. It might be interesting to see if those drop out of profiles. But I'm always curious about cases where people, maybe construct a std vector without reserving a certain amount of, or any I guess container, and not reserving a straightforward amount of size, and kind of overdo it with reallocations kind of thing. Is it's definitely curious.
So something we've been looking at in Google in that regard is that we have a type called inline vector. I think LLVM has a similar one, where the expected size of the vector is a template argument, and so it pre-sizes and you allocate into that memory. If it goes beyond that, then it starts to dynamically allocate. We have a thing that we call Risc-V, where on a function entry we sample the registers using a PEBS event. And so we can snapshot what the arguments to a function are. So, for example, we use this for spotting mem copies where you're copying size 0. And then we'll go and look through Google 3 and say, hey, that's a stupid thing to be doing. But yeah, we want to use that for kind of like pre-sizing inline vectors. And that could probably be shared work.
And I think one of the other interesting discussions that we had for areas of future research within Clang was kind of an architectural difference between Clang and GCC that has been, it can actually lead to not code gen bugs, but it can actually be problematic for having portable code between GCC and Clang. at least within the kernel, is that GCC tends to do some amount of early inlining and dead code elimination before performing semantic analysis. And so one of the things that's been supposed is, we spend a lot of time pulling in a lot of code from a lot of headers where we suppose that there's probably a lot of dead code there. And one of the things is that Clang will eagerly parse and perform semantic analysis on obviously dead code. And it will still perform the AST walk, it'll still generate LLVM. And then, we're kind of dependent on when does LLVM decide to do dead code elimination? And does LLVM waste time optimizing obviously dead code where after inlining, it would not have a route to, the entry of the translation unit or any externally visible symbol kind of thing. So I think one of the areas for future research that we've been discussing as a result of both those pain points trying to build the kernel with Clang, but also from seeing just how much time is spent in the front end, is the idea of, can we lazily parse maybe static inline functions in Clang? And there's been kind of, I don't know where the talk was given, but Chris Latner gave an interesting talk. His talk was focused on MLIR, but had kind of a footnote or ended the presentation with how might Clang leverage MLIR? Because Clang doesn't have another intermediary representation before it targets LLVMIR, but a lot of other more modern language implementations essentially do that also leverage LLVM. And he kind of had a blueprint showing, it might be interesting, rather than doing an AST walk to generate the code, could we use the control flow graph that Clang can generate to not emit, quite as much LLVMIR, or to emit more, maybe some level of optimized, like pre-optimized LLVMIR, which is certainly interesting.
Nick, Chris Latner made these comments in the introductory videos that explain MLIR when MLIR was first introduced. That way you should be able to find it.
Cool, thanks.
I had a quick question for.
Sorry, and if I can add quickly things, Chris also told me that he'd really love if somebody could take the time and retrofit Clang to use MLIR. So, that'd be a really cool intern project for next year. I'm just saying. Maybe we'd need quite a few interns to do that, but anyway.
I like the idea. Let's do it.
I was going to ask Huck, how many times when you, I know that this happened at least a couple of times, but cases where you were sort of like chasing down, interesting hotspots here, and then posted some of these findings, and then other people started jumping the gun to actually get ahead and fix it before you actually had time to go and finish the LLVM patches for it.
So the like x86 feature dependency bug, I think by the time that I had like enough time to look at it myself, there had already been like 3 patches submitted to fix various things there.
I mean, like literally we're looking at this exact profile view, and you can see here in this instance, get file ID local is 3% of an entire kernel build. Whatever that function was literally 13%, right? Big or thumb there, and that was being recomputed. Every GCC inline, every GCC ASM statement is the class in Clang, but basically for every inline assembly statement, of which the Linux kernel has a lot, we were doing some accidentally quadratic computations. And Fengrui, who's on the call, had a patch that I think it helped cut down on the complexity a lot. And then there was another patch from, I think, maybe the x86 backend maintainer in LLVM, Craig Topper, figured out how to cache this information kind of thing. But the kind of feature dependency stuff is there's a lot of microarchitecture extensions for any given ISA. In particular, a lot of like kind of SIMD extensions on x86 right? You have, well, anything, a lot of floating point stuff, right? So x87, MMX, SSE, SSE2, SSE4, AVX, AVX512, AVX2. There's a lot more FMA, all these things, and basically Clang really has to know what kind of environment it's targeting. For instance, Linux kernel will disable most of these to avoid having to save and restore potentially a large set of registers on every context switch.
Yeah, I just find it interesting because it's like, once you build these kind of enabling tools where, people can actually go and do performance analysis like in some reasonably easy manner, right? Because like the hard part here was getting all the Perfetto stuff in place and then sort of applying this to the Linux kernel. It's kind of like you can, then go chase interesting bugs in your own, LLVM code base, or find interesting things about your project, like why are we spending all this time doing a bunch of parsing? Like maybe I should restructure my headers, right? But we should definitely be using this as an argument towards like this is why the Perfetto patch should go in, right? I think that there's a compelling case here. You have enough data from this Linux kernel experiment to sort of drive the motivation for, hey, like this should be probably a premier feature of LLVM so that people can actually look at this over time, make sure that we don't slip in any regressions on things like that. So yeah, but really cool. Thank you.
Maybe two other notes about Linux perf. So in this trace, you can see here there's some unknown samples with very high addresses. So there's I'll send you the snippet, but I had to look this up myself. There's something in the kernel called kpointer restrict. The idea being is generally we consider addresses in the kernel to be a kind of private information that maybe user space shouldn't know about. And in fact, the kernel performs relocation on itself and is position independent because it does address space layout randomization, on itself. And we would so the offset of these kernel functions will change every boot, but the distance between any two addresses doesn't actually change. And Case Cook at Google is working on something called fine-grained ASLR to randomize every function, every global data in the kernel kind of thing. But basically, there's a syscontrol where you like echo 0 into a couple virtual files, and then suddenly now you don't get all zeros or like addresses that you can't symbolize in the trace. And so if you do that and then run, I don't know if you need to do that before running perf record or before running perf report. I just enable it, do both, and then turn it off. And I think the kernel function that shows up in the trace is basically just allocating new pages, right? Is the kernel is just pulling in a lot of pulling in like reading a file from source. Are there tricks we can do there? Maybe if we know we're running on Linux and like run mmap to try to map things in instead of paging them in on demand and having page faults and waiting for stuff. Maybe who knows? There's a lot of meat on the bone here. And then the other thing was there was another flag you had about no inline. So I think one of the issues we ran into was the use of LBR for collecting profiles. And one of the things we noticed here was that at least in our virtualized environment that we were providing interns for the summer, it seems like access to LBR was disabled. I don't know if this is something where generally the high performance hardware counters are inaccessible to virtualized guests or not, but we would get, I think there's an error message from perf if you try to use this. So you can flip to using the dwarf information instead, the dwarf debug info. And Clang is built with minimum line tables -GMLT, which is basically like Clang. If it does crash during compilation, it does try to unwind itself and print just function frame info. So that's good enough. You can actually use a release build of Clang. You don't need a debug you don't need a debug build, because even a release build of Clang will still have enough debug info in it to make this work. But no inline is specific to using the dwarf call graph, because dwarf will leave behind AT tags that say that inlining was performed here. And it will leave a lot of those behind. So like one of the things I noticed is when I was using LBR, no inline wasn't making as big a difference for me, but if you're using the dwarf call graph information, it sounds like that makes a dramatic reduction in perf report. Like how
yeah, I'll mention that as well with using dwarf. My traces of kernel compiles were like 50 gigabytes, whereas Nick using LBR had 5 gigabytes. So I essentially couldn't even do perf report on a full dwarf like kernel compile, because it would literally take like 2 hours even with the -- no inline to load.
And then wasn't there was another issue related to sharing the perf profile? Like not only was it 5 gigs to send you, but I thought perf report wasn't able to parse this.
So I guess as well, maybe perf report resolves like symbols against the original binary. I don't know. But when I would load Nick's traces, I would just get a bunch of junk. That would.
That's at that point we were like, wow, this Perfetto stuff is much more handy. Like, just send me the URL, please.
Yeah.
We have pprof, so pprof can ingest perf data files, and then you could share a URL for that. Uploading 50 gigabytes to pprof is probably quite painful.
Right, pprof was internal, and it needed like it could only. I thought it could only symbolize binaries that were built with Blaze or in Google 3, because there's like a symbol server or something already cached.
It does support not using kind of like symbolization on the host. My experience with that is that it's been broken, but it's a staffed Google 3 project, so you can file bugs.
Yeah, because Benjamin suggested the same thing, and I tried it and sent him the link, and he's like, "Oh no, this is all garbage in here. Like someone's not understanding symbols somewhere." And I think maybe pprof had a flag to you could pass it the binary, and I think that was still I don't know. It needs some more love.
Yeah, on the LBR issues, 5.8 has got LBR stitching. So one of the problems is that like at most the LBR call stack can be like 32 entries deep. In 5.8, there's now an ability to kind of like stitch together different LBR call stacks so that it can get deeper things. The guest support for LBR is something that's been worked on upstream. The patches for that haven't landed yet. So yeah, that's broken. We have been adding benchmarks to perf for like stuff that's slow. And so it would be good to get some of these cases added as benchmarks to perf, because at least we can stop it from getting slower. And then we can also profile perf and go after low-hanging fruit.
You're going to profile the profiler? Meta.
I think
I look forward to testing out the perf stitching. I think one of the issues is probably the environment that we were running this in maybe didn't have 5.8, but we've definitely seen some anomalies in some of the trace data for either deeply recursive functions. I'm guessing, maybe overflow that LBR buffer, or like a couple of cases where something that's obviously a leaf, like a child, kind of the final stack frame being higher up in certain places than we expect. Something where it looks like something either like the trace wasn't captured correctly, or maybe we overflowed a buffer, kind of thing. But
there are issues. I mean, there's an issue with the frame pointer based unwinding that because the frame isn't established at the first and the last instruction, then it actually thinks that the caller is kind of like one higher than it should be. generally LDR is much more accurate than that because it can even work through things like tail call elimination. But, yeah. Please file bugs on it. We'll try to get to them.
Any other questions for Huck? All right. Well, as your mentor, thanks so much for all the help over the summer, Huck. I hope you had fun with a lot of these projects, and I think it gives us more work to do now. Now we have a sense of how do we hunt for the bugs, and we've got plenty more to do to dig in now and start fixing these. So thanks for taking the time to investigate all these things, to get Risc-V booting for us, to fix these, unwinder ambiguities, and finally the Clang-tidy Clang analyzer stuff is really dear to my heart, because I think like 3.5 years ago when I started this project to build the kernel with Clang, I only really wanted to run this scan build, right, Clang's static analyzer on the Linux kernel, and kind of found out that was predicated on being able to build the kernel with Clang, and then I'd been distracted off in the woods, kind of fell into a very deep pit there. So I'm incredibly proud that you were able to kind of wrap up this work and finally get it working. And I'll just allude to people on the video that it's finding bugs, so we should take a look at these reports and go fix them. Cool. Thanks.
Cool. Yeah. I guess that's it. If